We now have the following proposition. Let omega contained in Rn be open, then L1 of omega is not reflexive. So we saw that all the LP spaces 1 less than P less than infinity were reflexive, and we said nothing about L1, and so L1 is now we show that it is not reflexive. Okay, so proof. So without loss of generality, we can assume that 0 belongs to omega. So you can translate, and by translation you lose nothing. Lebesgue measure is translation invariant, and therefore we can always assume that omega contains the origin. So let n be sufficiently large such that b 0n, the ball, not n, 1 by n is contained in omega. Okay, so all sufficiently large this thing. So let us assume that alpha n is the Lebesgue measure of Bn, so call this Bn power minus 1. Okay, so and then you set fn of x equals alpha n for all x in Bn and 0 on omega minus Bn. Okay, so this function then fn obviously belongs to L1 of omega, and in fact you have integral mod fn dx over omega. This is nothing but the integral over Bn, everywhere else it is 0, and that is alpha n dx. Alpha n is a constant, it's alpha n mod Bn, and that's equal to 1. So norm fn 1 is equal to 1 for all n. Okay, so if L1 omega were reflexive, there exists a weakly convergent subsequence. So we have seen that any bounded sequence in a reflexive space has a weakly convergent subsequence. So let us assume, if possible, let f and k weakly converge to f. Okay, so this means that is for every h in the dual space, which we have seen is L infinity of omega, you have integral f and k h dx over omega converges to integral f dx over omega. So if I take h to be identically 1, this L infinity function, this means 1 equals integral omega f and k dx. This this is fh. This converges to integral f over omega. So this implies that integral over omega f dx equal to 1. On the other hand, let us take consider h belong to Cc of omega minus the origin. This is also an open set. Okay, so and this of course is contained in Cc of omega. Okay, and it is also a L infinity function because it vanishes outside a compact set, and then so this is also in L infinity of. So you can put h there. Then so what do you have? You have omega, whereas the origin is here, and then you have omega minus 0, so we have removed this point, and therefore you have a function which has compact support outside this. So if n is sufficiently large, then the Bn and this support will not intersect. Then for k sufficiently large, support of H intersection B and K will be empty. Okay, so this implies that integral f and k h over omega equal to 0, and this implies therefore the integral fh over omega equal to 0. So f is what? F is L1 function in omega, and therefore, and for every h in cc of omega minus 0, integral fh is 0. So by the theorem which we proved, we have, this implies that f is 0 almost everywhere in omega minus 0, because for every continuous function with compact support, integral fh is 0, and this is compact support in omega minus 0. But then if you add 0, that's still a set of measures 0, so that is f equal to 0 almost everywhere in omega. But that's a contradiction, because integral f equals 1 and f equal to 0, so this is a contradiction, and therefore you cannot have a weakly convergent subsequence for this sequence, and therefore L1 is not reflexive. So corollary, omega contained in Rn open, then L infinity of omega is not reflexive. So this is immediate, because if V is reflexive, V star is reflexive, and conversely, and therefore L1 of omega is star is L infinity of omega. L1 is not reflexive, therefore L infinity cannot be reflexive either, because it's an if and only if condition for the dual for reflexivity. Therefore, to sum up, we have LP of omega equals L P star of omega, 1 less than or equal to P less than infinity. P star is the conjugate exponent. This is not true for L infinity. We have not proved it. We will see in the exercises actually that there is a continuous linear function we will do. But then you have that LP of omega reflexive and separable if 1 less than P less than infinity. L1 of omega is separable but not reflexive, and finally L infinity omega not separable, not reflexive. Okay, so this is the summary of all that we have done so far. Okay, so now we will conclude with an important inequality. Okay, so theorem. This is called Young's inequality. So let 1 less than P less than infinity, let f belong to L1 of Rn. So we are now in the entire space L1 of Rn, and G belong to LP of Rn. Then the map x going to integral over Rn f of y g of x minus y dy is well defined for almost every x. Okay, the function thus defined is called the convolution of f and g, and is denoted f star g. Okay, further f star g belongs to LP of Rn, and you have the Young's inequality. Norm of f star g in LP is less than or equal to norm f1 in norm GP. Okay, so this is called Young's inequality. Okay, so proof. So let H belong to LP star Rn. P star is the conjugate exponent. Then you consider the function xy mapping to f of y g of x minus y hx. So this is measurable in the product space. Okay. Now you consider the iterated integral. So consider I to be equal to integral Rn. The integration is with respect to x, so that I am indicating here, and then integral Rn, the integration is with respect to y. So mod fy g of x minus y hx modulus dy dx. So first integration is with respect to y, then the integration with respect to x. This is well defined because we are having a measurable function and modulus is non-negative, therefore you can do. So Lebesgue measure is translation invariant. And we can also interchange the order of integration because you have a non-negative function. Fubini's theorem says that I can interchange. So I get I equal to integral Rny mod fy integral Rnx mod g of x minus y hx dx and then dy. Okay, so I can, if you want, you put a bracket like this. So you're first integrating. Now here you have G is what? G is in LP and H is in LP star. So by Helder's inequality, this is less than or equal to integral Rny mod fy into whether you have, since y is now a fixed constant, so you are just translating the origin for this function, and therefore that's why Lebesgue measure is translation invariant. So this will give you a norm GP, norm H, P star. But these are constants which come out, and therefore this is less than or equal to norm GP, norm H, P star. Then integral mod Fy is just norm F in L1. Okay. Okay, and that is of course finite. So by Fubini's theorem, Fubini's theorem says if the iterated integral with the modulus is finite, then for almost every x we have integral Rn f of y g of x minus y h of x dy exists. That is part of the Fubini's theorem. When you have the iterated integral with the modulus is finite, then each for almost every value of one variable, the function in the other variable, the integral will exist, and therefore this exists. Now you choose. Here you notice that h of x doesn't depend y, it doesn't depend on y, so it will come out of the integral. So h of x times this integral exists. Now you, for almost every x. Now you choose h of x in LP star Rn such that h is not equal to 0 for all x. h of x is not equal to 0 for all x in Rn. For instance, you can take h is equal to e power minus mod x square. So this is, for instance, a function which will never vanish. It's in all the LP spaces, and therefore you can choose this as it. So then you can divide by hx, and therefore this implies for almost every x we have that integral over Rn of f of y g of x minus y dy exists. So that mapping is well defined, and therefore the convolution is also well defined. Now we also consider h going to integral Rn of h of x f star g of x. So what is f star g of x? This is nothing but integral over Rn with respect to x, integral over Rn with respect to y, h of x f of y g of x minus y dy and then dx. Okay, and that we saw. Therefore this is such that it's a continuous linear functional on LP on LP star Rn, because h goes to this continuous linear functional, and modulus of this, so modulus of integral h of x f star g x dx was less than or equal to, we just calculated it earlier, namely this one. Therefore you have norm h in P star, norm f in L1, norm g in P. Okay, and therefore this is a continuous linear functional, and hence by the Rees representation theorem, this 1 less than p less than infinity. So f star gx belongs to LP of Rn, because that's the dual of LP star, and you have norm of f star g in LP is less than or equal to norm f1 norm gp, and that is exactly Young's inequality which we wanted to show. Okay. So remark, so by a simple change of variable, we also have f star g of x is equal to integral over Rn f of x minus y gy dy. Second remark, Young's inequality also true for p equals 1. Okay, so if f and g are both in L1, f star g is well defined by the, and we will you have norm of f star g in L1 in less than or equal to norm f1 norm g1. This is true, and we will see it in the exercises.